Hello everyone, you're seeing this video and through PlayPosit because of the fact that I will not be in on Thursday, September 27th. So I wanted to give you an additional guided lesson, so to speak, even though I won't be in to conduct it. So this is more or less set up so that if you complete this PlayPosit, which has the same questions that are posed to you in EDIO, you'll also get credit for attending the guided instruction. You could not mark the ones in EDIO, whichever one you want to do. But I'm only going to do that until the end of next week because PlayPause only keeps the video for so long. So, after a certain point, I'm not going to be checking anymore if you haven't attended the guided instruction or you haven't completed um, the PlayPosit by, we'll say, the end of September. We'll say September 30th, or no, October 1st, just to be on the safe side. Then you have to complete the work in EDIO to get credit for participation. But anyway, let's get into the lesson itself at this point. So in the previous lesson, we used an interactive Rodney breaking these boards, and mostly to help us introduce ourselves to the midpoint formula. How to split something in a 1-to-1 ratio, exactly in half, two equal parts. Well, what if you wanted to break them and not be equal parts, but you wanted to have a particular ratio, like a 2-to-3 ratio or a 3-to-4 ratio? Well, there are some similar methods for doing that. So to kind of introduce those methods, you're going to work with another interactive, which is very similar, except it's now going to, it's called Let's Break Some Boards 2. And basically, it's going to have you split these boards in not only 1-to-1 ratios, which will still show up, but they'll also have you doing other ratios as well, and you have to devise a way of doing that. So, at this point, I want you to pause for a moment. Pause this PlayPosit. You'll have a reflective pause. Go to the interactive on page 2 in EDIO. Play around with it for a little bit, and then come back and continue the video, and answer the questions that I'll be posing to you along the way. Okay, welcome back. So, based on your work with the interactive, and if you haven't done any work with the interactive, please pause again right now, go back and do it. Hopefully, it will give you some insight how to answer these questions. There are 6 students down here, and each one's describing a method of how they would determine the breaking point of a board if they want to split it into a 1-to-2 ratio. Or basically, if you're just taking a line segment of a specific endpoints, how would you break that into a 1-to-2 ratio? Each one's describing methods here that could or could not be correct. I want you to see which of these would be correct. So make sure you read them very carefully, consider what they would do, and then pick the ones that you feel are the ones that would give you a 1-to-2 ratio. Okay, so now that you've had a chance to answer, let's walk through these. Basically, the ones that would give you a 1-to-2 ratio are the descriptions given by student 2, student 3, and student 5. You have to remember a 1-to-2 ratio, a 2-to-1 ratio is considered to be the same thing in many aspects. I mean, you still have two pieces that one's basically 2 times bigger than the other one. That's essentially what's going on with that. So now, as far as the incorrect one, student 1, if you actually follow that methodology, you would have a point that's no longer on the segment. It could be like, beyond the endpoints. It could just even be floating above the segment. And one of the things that, these breaking points that we're talking about, like the midpoint, it has to fall on the segment. So, and that happens with student 6's description as well. Again, you would have a circumstance where it would no longer fall on the segment. Now, for student 4's description, basically what it would do is it would give you the x-coordinate of the midpoint, and it would give you a y-coordinate that equals the y-coordinate of whichever one had the smaller y-coordinate. Um, and again, that's more likely going to be a point that's actually not on the segment anymore. And even if it was, it would more than likely be at one of the endpoints of the segment. And the endpoint is not, it's an endpoint. You can't break it at the endpoint. So, so that's what's going on in those. The other three, those are the ones that each one of those would produce a 1-to-2 ratio or a 2-to-1 ratio, which, again, as far as distances goes. Um, so, so now answer this question using some of the ideas that you came up with this. Suppose a new board has endpoints at 3, 4, and 11, -2. Which of the following would be the coordinates that partitions the board at a ratio of 2 to 3? So pause a moment, select all those that apply, and then we'll go over it again. Well, as mentioned before, there should be 2 points that split the boards into a 2 to 3 ratio. In that one side and another side has this 2 to 3 ratio. Again, a 3 to 2 ratio, 2 to 3 ratio, they're considered to be the same thing because as far as sizes of your pieces. You just have to make sure that depending on how it's communicated, whether or not you need to have the shorter side be a specific part of it, or a longer side being a specific part of it. The way that these lessons are kind of working, no, it doesn't. I mean, so oftentimes there's only going to be one midpoint. There's only going to be one point where you get a 1-to-1 ratio, but there's any other ratio, you're typically going to have more than one point to do it. So to kind of go through how to go through these, what I did is, I first realized that with a 2 to 3 ratio, that the proportions of the pieces, if I was looking at the total length, that, if I split it a 2 to 3 ratio, one piece would be 2/5 the size of the original piece. The other point would be 3/5 the size of the original piece. So what I want to do is figure out, okay, well, I know I'm either going to move 2/5 of the way from one point to the next, or 3/5 of the way from one point to the next, and it really depends on how I choose to handle it. And there's variations that you can do because, as I said, you could start with the smaller x coordinate and add a certain length to it, and start with the smaller y coordinate and add a certain length to it based off of whether it's a 2/5 or 3/5. To find the point, you can start with the largest coordinate and subtract from it, or you could do one, for the x and one for the y. I mean, there's different variations of this. So, what I'm showing here in a moment is not going to be the only option. So the first thing I did is I decided I'm going to use the 2/5 ratio and say, okay, starting with the smaller x coordinate, 3. 3 and 11. I'm going to find 2/5 of the distance between the 11 and 3 x coordinates. Take 2/5 of that and add it to the smaller x coordinate. So I got 6.2 when I did that. And then I took the smaller y coordinate, in this case -2. Notice they were different coordinates. I mean, they're in different pairings. I just want to make sure I know which one is, when I do x's, which one's the furthest left, which one's the furthest right, so that I'm going to be adding to the one that's furthest left. And when I look at the y coordinates, I'm looking at which one's on the bottom of the segment, which one's on the top, and who's going to add to the one that's on the bottom. So to -2, I'm going to add 2/5 of the distance from 4 to -2, and I calculate that to get 0.4. And then I do something similar for 3/5. Just doing the same thing, applying the 3/5. Again, we're starting with the smaller x coordinate, the smaller y coordinate, and I get 7.8, 1.6. As I said, other options are I could have used the larger x coordinate and the larger y coordinate. The only thing that'd be different is that I would need to take away from it, because remember, these are endpoints. I need to be working in the opposite direction. So if I have the endpoint that's on the right, I know I have to move left for me to find these breaking points. If it's the endpoint, if I'm at the higher endpoint, I know I have to move towards the lower endpoint in order to find that breaking point. So other options I could have used for this were to do 11 minus 2/5, 11 minus Uh, and 4 minus 2/5 times 4 minus -2. Um, or I could have done 11 minus 3/5. As you see, I get the same coordinates. I mean, so there's only going to be two breaking points, no matter which way you calculate it, and there's different methods you could find it. So you just have to be careful that you know which point you're working with and which way that the breaking point has to be with respect to that point, whatever it may be. So all this board breaking has made Rodney realize he wants to develop a rule or a formula. So as you see here, Rodney developed a formula, but the referees also developed a formula to determine whether or not they have this ratio correct. So, obviously the formulas are a little bit different from each other. Now, if you look very carefully, Rodney's is very close to what we've been doing because the A over A plus B are essentially the ratios or the proportions we get from the ratio, and then we're making sure we're adding it to a specific coordinate. But notice that they had the subtractions clearly defined. The reason why these formulas work is because, if you do x2 minus x1, if x2 happens to be smaller, then I'm going to have a negative, and I'll be subtracting. So if I do have the bigger x coordinate there, I will be subtracting. If I have the smaller one for x1, I'm going to be adding. So that's why these work out the way they do. So, but Rodney's is very close to what we were doing. We want to see if the referees will do the same thing. So first off, we're going to use Rodney's formula to calculate the two coordinate pairs. So take a moment, find the two coordinate pairs that's going to break this or partition this segment into a 2:3 ratio. Okay, so applying Rodney's formula. Now there's different variations to this again because what I let A and B be is different. What I call x1 and x2 could be different. As I said, if I switch some things around, I'm only gonna get one of two potential coordinates. I just have to make sure I'm consistent across the board. So when I do my first calculation, I'm assuming x1, y1 is 2, 5, x2, y2 is 14, 17. I'm looking at A being 2 and B being 3. And when I put those all together, I do 2 plus 2/5 times 14 minus 2, I get 6.8. And for the y coordinate, I get 5 plus 2/5 times 17 minus 5, which is 9.8. The next thing I can do is I'm just going to say, okay, well, instead of calling A2 and B3, I'm going to call, B2 and A3. And now I'm going to have the 3/5 ratio working off the same type of thing. Again, once I call one of them x1, x2, so my options are either to change around this ratio, or I could change around what I'm calling x1, y1, and x2, y2. Because remember, these are rather arbitrary. What I'm assigning to be x1, y1, what I'm assuming to be x2, y2 is arbitrary. What I'm just assigning to A and B is also rather arbitrary. It doesn't really matter which one I'm assigning as long as I'm consistent across the entire calculation. So if I just switch around the definitions of what A and B are, I also get 9.2 and 13.2. So, and that's using Rodney's formula. Let's see what happens if we use the referee's formula. So I want you to use the referee's formula, see if there's any consistency with this or if you get something else, and we'll check with you in a moment. So here's the referee's formula. Looks a little more compact, not as much parentheses and different subscripts, but you still see some of the work there. So if I plug it again, I'm going to let x1, y1 be 2, 5, x2, y2 be 14, 17. I'm going to let A be 2 and B be 3. And I'm just putting all those values in where they belong. So I have 3 times 2 plus 2 times 14 all over 5. I have 3 times 5 plus 2 times 17 all over 5. And I get 6.8, 9.8. And again, as I said, I could either switch the definitions of what x1, y1 or x2, y2 is, or switch what A and B are. If you switch both, you'll probably get the same coordinate again. But if I just switch what A and B are, Some of the numbers changed a little bit as far where they're at in these calculations, and I end up with 9.2, 12.2. So what you should be noticing at this point is that I got the same coordinates, the same two coordinate pairs from both formulas. That's evidence to suggest that these two might be um, equivalent to each other. So what I want you to do is pause for a moment, see if you can come up with a means of showing how Rodney's and the referee's formulas could be the same thing. Very similar to something we had done in the previous lesson when we were comparing Rodney's midpoint formula to the referee's midpoint formula. So hopefully you had a chance now to come up with an attempt to see how you could show that these are the same thing. That these formulas produce the same thing. They are basically equivalent to each other. One's just another version of the other. I'm going to show that using the video that I actually have in the lesson itself, because I designed it. It's still me talking to you, so I could use it. So let's have a look at it. So with this proof right here, and this is a proof that's a little bit beyond what you're going to be expected to do, especially with all the subscripts. I mean, with all the subscripts, that could be a little bit much to do. But everything that you've seen there are basically rules of fractions, additions, subtractions, and things like distributive property. So it's nothing that you haven't done before. It's just with all the symbol use, you might think it's something you've never done before. So keep in mind that that basically that there's no particular reason that you have to know how to do this proof, but just know that now we have a proof here that says that they are the same thing. And that brings us to the end of what you had to do for this. So um, to wrap everything up, make sure that you do take any notes or anything that you want to on page 14 of your workbook, and make sure that you do page 17 of your workbook. That will eventually be collected for sample work under this topic. But that's all we have. So if you have any further questions, please make sure to touch base with me at some point in time. I will be back on Friday for live classroom time. And if you have any questions, you can also bring them up as we start that off. Until next time, have a good day, everybody.